Earlier, we discussed the incredible evolution of language models, from statistical modeling and basic tasks to advanced neural networks and LLMs. In this lesson, I would like to explore the world of language modeling more, adding technical detail to the picture. This will help improve our overall understanding. We'll describe 4 core techniques used for language modeling throughout the years, and how each solved the preceding issues. The first technique, N-grams, is a fundamental building block for language modeling. The idea behind N-grams is pretty simple. We can estimate a word's probability based on the preceding n-1 words. So, in an n-gram with n equal to 1, called a unigram, 1 minus 1 would equal 0, right? This means that the prediction is not based on any context. Let's see how this works. We have the following sentence, and aim to predict the final word. The n-gram model functions by not using any words from "my favorite sport is" to predict basketball. Instead, it would review the entire text and look for the word that appears most often, assuming that the word with the highest frequency is the best bet to fill the blank space in the sentence. So, the unigram model might predict common words like the or and, regardless of their actual fit with the previous words in the sentence. But if n equals 2, called a bigram, the prediction of basketball depends solely on the previous one word. In my favorite sport is, we focus on is to analyze the frequency of all subsequent words in the training data. The same goes for a trigram. The model analyzes instances of sport is in the training data to predict the most frequently occurring subsequent word. So this is how n-gram works. Far from ideal, huh? The model seems to miss the subtleties of context and prior information. It simply aims to optimize predictions based on appearance frequencies in the training data. Neural nets are undoubtedly a giant leap forward. Recurrent neural networks, or RNNs, are neural networks that work best with text. A key strength of RNNs is their ability to retain information from prior steps in the neural network. Analyzing previous words in a sentence helps the RNN network decide on the next word. This is a considerable breakthrough compared to n-gram models because the order and context of data points are crucial when dealing with language. The primary challenge with RNNs is their difficulty in handling large texts, as they tend to lose earlier information with progressive text segments. This problem is called the vanishing gradient issue. To solve this, AI scientists developed long short-term memory, or LSTM networks. LSTMs improved traditional RNN models by introducing a gate architecture to choose which information to retain and which to discard. This allows the network to keep important long-term information and forget irrelevant data, which makes LSTMs significantly better at tasks involving complex text data. The main drawback of LSTMs is their high computational cost and slow training speed on large datasets, making them unscalable. But in 2017, the paper "Attention is All You Need" introduced the concept of transformers and the attention mechanism. The attention mechanism allows a model to assess the significance of various words, or parts of words, or tokens in an input sequence to generate an output. Therefore, the model identifies key words and focuses more intensely, lowering computational costs and enhancing scalability. Transformers process text by selectively focusing on relevant sequence parts at each step, rather than handling the entire text simultaneously. This is achieved by assigning an attention score to each word in the input sequence. Words with higher attention scores are deemed more significant, enabling transformers to handle long-range dependencies. Okay, great. So now you know how we got the technology that made the creation of LLMs like ChatGPT possible. We're making excellent progress. In our next lesson, we'll discuss different phases when building an LLM. Thanks for watching.